Good morning. I wanted to briefly go over with you the second group of readings over plate tectonics that are associated with Module 3. And I'm going to tackle these topics right in here. And I'll be posting the video right in here. And then I also will be putting them under, I'll make sure that this video is also posted under the Geology Part 1 videos. Actually, I think they're under the lecture. Let me see here. Geology Part 1, Geology lectures. Yeah, under the Geology lectures, I will be putting this under the Geology Part 2 lectures right here. So you'll have a couple places where as you're going over these readings, I'm going to be highlighting some of the concepts I want you to be aware of and be thinking about as you're going over these readings. I won't be long, but this unit is, or this topic is about how the Earth's crust and the outer part of it, which we call the lithosphere, is basically in a constant state of motion. And this motion, which we'll have different terms for, called plate tectonics, continental drift, seafloor spreading, are all indications that the Earth crust is dynamic and moving. And it's these movements that really are the foundations of the field of geology. So as you're going through these readings, you're really getting the hallmarks of really what is the signature concepts of what creates the geography and the variations in the way in which we see landscapes across the Earth, being mountainous, valleys, glaciated terrains, the very nature of how the continents are shaped and their distribution from one another, the size of the continents and the oceans that separate them. They're always in a constant state of flux because we have learned through a series of evolutionary theories that the Earth's crust is dynamic and moving, and we're going to kind of go over some of the processes that shape those movements and patterns and how this whole idea came into existence. So to get an idea, you have to get an idea, and this will be a major topic with the lab on earthquakes, that if the Earth's crust moves and the lithosphere is the outer shell with the upper part of the asthenosphere, which is sort of molten rock, that when the Earth's crust moves, that energy is dissipated in a series of waves called P and S waves. These P and S waves move at different rates, and as you'll read, that this is what really creates earthquakes. And this is how we know earthquakes are a direct reflection that the Earth's crust is moving. And the difference between how the S waves and P waves move by speed is how we can calculate and triangulate where an earthquake started or happened. And when you do the earthquake lab, you will literally be using the difference between the primary waves and the surface waves, and you'll be understanding and evaluating that earthquakes are ultimately the reflection. And when you find out, you're going to see that earthquakes and volcanoes, for example, which are driven by plate tectonics, is very much driven by the idea that the Earth's crust is constantly in a state of movement and flux. And you'll be really getting into that concept about the Earth's interior and how energy moves with the earthquakes lab. Now, to understand plate tectonics, you have to understand the structure of the layers of the Earth, from the inner core to the outer core to the mantle to the outer mantle, and then the crust with the asthenosphere, that temperatures increase as you go inwards, and so does pressure. And constantly this energy and heat is trying to dissipate outwards, and the Earth's crust has to find points and cracks to release that energy and pressure trying to escape. And that's what inevitably is what is creating the whole idea of plate tectonics and the idea that the outer shell of the Earth is sliding around the planet because energy from inside the Earth's mantle and the core are pushing energy and heat outwards, and the Earth's crust has to find weak points and cracks to allow that energy to dissipate. So it's very important to understand this sort of structured layer that we can literally see the Earth's interior, just like the atmosphere, is stacked into layers, and we're really only familiar with the outer shell or the crust, which we live on, but what is happening on the Earth's crust is so much dependent upon the energy and the layers beneath us trying to dissipate energy and heat out. So make sure you can kind of see by scale kind of how the Earth's crust, and you can see that the outermost part where we are at is very, very thin in relation to the other layers underneath. When you look at the core, the outer core, and this isn't even to scale, these layers are generally much deeper underneath us in terms of their, and the densities change as well. As you look at the Earth's structure, the further you go down, the heavier materials and minerals and elements have drifted down towards the middle, and so that's why you find the core will be the heaviest rocks, and as you move outward, the lighter materials have floated to the top. So the Earth's crust of where we're at is actually some of the lightest materials in the Earth's interior. So make sure you read, and a great little video here that I would go over, and this really quick video puts into action what these layers look like underneath, and you can kind of see the layers as they would be in dynamic motion. When you see what is underneath the crust and how thin the crust is compared to the mantle underneath it, you'll really be getting an idea of how sensitive the Earth's crust is to the amount of energy trying to escape from the interior. So make sure you watch this video here, very nicely rehashing these layers and how the Earth's crust where we live is tied to the layers underneath us. The whole idea of continental drift happened, really in the 1900s, in the early 1900s by a German, I believe, maybe the correct pronunciation is Alfred Wagner. Some people might say Wagner. And the idea was that he was kind of an amateur paleontologist, and he was trying to figure out how would you find species of dinosaurs on different continents when these continents today are all separated by oceans. When he looked at a globe and a modern map, he kind of see how different continents were fitting together like a jigsaw puzzle, and he proposed that, in fact, all of the continents were together and tied together in one piece called Pangea, or Pangaea, depending on your pronunciation, but I think it's Pangea. And he actually proposed the idea that the continents were constantly adrift, and that, in fact, at one time they were all kind of tied together, and that's why we could find dinosaur fossils in multiple continents, because they could actually, in some places, walk from one continent to the next because they were all bridged together. And so this theory did not go with a lot of acceptance, and because he couldn't really prove it. But about 50 to 60 years later, with the rise of submarines moving around the Earth and mapping the ocean floor to make maps so the subs can navigate the ocean better and not hit the bottom of the ocean, through the use of new technologies like sonar, we began to see maps that actually revealed 50 to 60 years after Wagner died. We ended up finding out that the proof and evidence that the continents was moving was actually there the whole time. We just didn't have the technology to see that. And you'll see the upcoming slide that continental drift and plate tectonics really did not take hold till the 1950s and 60s, with the evolution of maps being generated off subs with sonar maps. And what we ended up doing is, as we were making maps of the ocean floor with submarines, sonar maps would map electromagnetic waves off the bottom of the oceans, and then depending on how deep the oceans were, it would take longer for if it was deeper, and it would take less time if it was shallower. We ended up finding out that there were these massive mountain ranges on the floor of the ocean called seafloor spreading centers, what literally looked like cracks opening up. And then as these maps began to be made, some of these early maps some people would actually look back and actually refer to the theories proposed by continental drift by Alfred Wagner 50 to 70 years earlier, and they started to propose that in fact all of these continents, Africa, South America, North America, and Europe, they used to be actually all together along this seam here on the North Atlantic and the Mid-Atlantic ridge. And so actually the opening up of the seams that actually revealed that the Earth's crust was actually being exposed and revealing that it was moving did not happen to about 50 years. And indirectly, Alfred Wagner's plate tectonic theory was actually proved many decades after his death with the evolution of new technology, and it literally led a whole new area of science where we proved that along these cracks we were seeing regularly very new crust as magma was being pumped out, and it was sliding older crust to the margins of the ocean basins. And we were literally producing maps showing almost like a conveyor belt that the oceans here, that the Atlantic Ocean is opening up and becoming bigger and bigger and widening every year, with the newest rocks on the planet being found and these seams opening up with magma rolling out. This was the beginning that we realized that we actually had these trigger points that were starting the Earth's crust start to slide and move. And where there would be new crust created, we would find out that there would be on the opposite margins old crust being destroyed. And so inevitably we had the beginnings of what would be modern geology. And so they kind of show you this in a picture here, that there are basically kind of like different ways in which plates start to interact. And we'll see this with later slides, that if we have a seafloor spreading center, wherever there's a new crust being created, there has to be another place where older crust is being destroyed. Because as space is being opened up along a ridge, there has to be another place where, as the oceans crust are moving, there has to be another place where old crust is being recycled and destroyed. And that gets us today to seeing our modern maps through many decades now in mapping. We now realize that the Earth is made up of a handful of 12 to 15 tectonic plates, that each one of these plates is moving around the Earth and interacting with the plates along their margins in different ways. It'll be very important for you to pick up and capture that generally all along the margins of each plate is where either you will see plates sliding with one another and converging. In some places, they're sliding by one another. In other areas, like often on ocean floors, we actually see the ocean floors opening up and splitting and diverging. Depending upon where you are along these boundaries, you will see different types of geologic phenomena, but generally for our class, it is along these boundaries that we will see mountain ranges forming, earthquakes happening, and active volcanoes and dormant volcanoes forming. So we live on the North American plate, and obviously we can see the North American plate interacts on its western margins with the Pacific plate, and then you can actually see in the middle of the Atlantic Ocean that the Eurasian plate comes into contact with the North American plate. And you will see throughout many of the exercises and themes we will be studying that the most interesting and fascinating geologic phenomena in these regions are often occurring along the boundaries where tectonic plates are interacting with one of three types of interaction. So again, make sure, if you're a visual learner, these videos that are embedded on here kind of give you a visual of what you're looking at here in these stationary maps. One of the key themes is understanding that there are three types of plate boundaries, as I discussed earlier. So when we see the Earth from like a sonar map showing you the terrain of the ocean floors, we actually see that the tectonic plates interact in one of three ways. And depending upon where you're looking at, you will actually see convergent plate boundaries where two plates kind of slam in together. That's where you're going to find a lot of mountain ranges and volcanic activity. Divergent plate boundaries are where we see the Earth's crust opening up and plates are moving, separating from one another. And here's the most famous divergent plate boundaries in the middle of the Atlantic Ocean. And the Atlantic Ocean is literally forming as Pangea broke up. The Atlantic Ocean is continually getting larger as Africa and Asia are moving away from North America and South America. And all of these continents actually used to tie together right along this seam. And so transform boundaries are where we actually see two plates sliding by one another, and these are often famous for earthquake activity like the San Andreas fault line. When you look at a globe, we can actually see Africa is going to be an area that is breaking up, and is actually these lakes in the middle of Africa are forming as Africa is splitting into two separate continents. And from Earth, we could actually see some of this visual phenomena from space. For example, here is two plates colliding in the Andes Mountains. South America is actually colliding with the Nazca Plate, and you can literally see the Andes Mountains are forming as two plates are interacting and hitting one another. I will have some videos, so when you're talking about these different types of plate boundaries, we'll immediately have some red flags of the types of geologic activity associated with each. Okay? And so there's some pictures here. Here's a famous one. This is the San Andreas fault line, I think in California, where you're actually seeing one plate moving one way and the other plate sliding the other way, and they're sliding and grinding by one another. And you can see visually in some parts of the world, tectonic plates are actually visual at the Earth's surface. Because the tectonic plates are constantly moving, we can see areas and mountain ranges and oceans are constantly in a state of flux and change. One area that was once an ocean basin can now become a mountain range, and some areas that were mountain ranges can be relocated and eroded away to become the bottom of the ocean. So when we look at the Earth's changing surface, I have a video that I'm going to direct you to that really kind of shows you the history of the Earth and how dynamic plate tectonics has been to reshaping the globe we see today. And I'll point that out here at the very end to you. The last slide that I want to look at today is this video is missing, okay? And it really kind of puts together everything we've talked about with the plate boundaries, the energy that drives the plates, the history of Alfred Wagner. And I want to show you where, I would say you would want to start looking, finish off your readings. And if you're a visual learner, if you look under the Geology Part 1 videos, there is the Earth's layers, tectonic plates, and the rock cycle, the different types of plate boundaries, and the associated geologic features. But this gets in very quickly.
Those plates, creating convection.
They kind of talk about what happens at a convergent boundary versus a divergent boundary versus a transform fault. And they actually can kind of explain to you what you're going to be expecting to see when you study and do some of the exercises about geology. Now, this video is the history of plate tectonics sped up. And if you're fascinated about the history of the Earth and science and nature and how species have formed and evolved over the history of the Earth's history, this video really ties together, and it's a nice little movie, and you could do it in parts. It literally shows you how Earth's internal energy and plate tectonics can be used to reconstruct the entire history of how the Earth has physically changed in its appearance, and ultimately how these changes led to changes in the biosphere and life. So these 4 videos are just really nice rehashes if you're a visual learner of everything we're talking about in the first half of the Unit 3 readings. Those readings there will really cover all of the ones down through Section 2 and Section 3 here. And so I'll be doing a video on Section 3 probably tomorrow. maybe later this week, but I'm going to go ahead and stop this video, and this video will be posted right here, and you will also see this video posted, this lecture video will be posted under the Geology lectures. This will be the Geology Part 2 lecture. So I will stop this share, and I'll get this put on the YouTube here real quick. And I'll end this recording, and then hopefully this will help you learn about what your concepts are for Unit 3 here on plate tectonics and plate boundary types.